This lesson is part 5 in a series on statistical analysis of data. In this video, I'll be looking at ways for us to apply summary statistics to quantify the precision and accuracy of measurements. An important part of measuring is the numerical value of the measurement. However, the value is meaningless without units. Be sure to always include units when recording measurements. A measurement is never certain. There are always errors in measurement, even if they're very small. It's important to know the level of error that may be inherent in a measurement. A measurement is only useful if a value is associated with units and the uncertainty of the value is understood. Potential error in a measurement creates uncertainty. There are two types of errors that can occur in measurement. Random errors are typically associated with the measuring equipment or the person performing the measurement. For example, when measuring the volume of a liquid in a graduated cylinder, the measurement value may fall between two graduations on the cylinder. The reader must estimate the value to the nearest increment on the cylinder, which may sometimes be too large or too small. Random errors can usually be identified by repeating the same measurement. Systematic errors are more difficult to identify. For example, a person timing heats of a track and field race stands 100 meters away from the starting gun. Since it takes some time for the sound to travel to the person timing the race at the finish line, the timer consistently depresses the button to start the stopwatch a fraction of a second later for every race. For another example, a scale is not zeroed before taking measurements and is later found to read 0.2 grams with no mass on the scale. Therefore, all the measurements consistently show a mass of 0.2 grams greater than the mass of the object measured. Systematic errors can be eliminated if they're identified, but they're often undetected. We know that errors always exist in measurement. Therefore, there is always some uncertainty associated with a measurement. We never know the true value of a measured quantity, but we can get closer measurements with more precise measuring tools. But even with the most accurate and precise measuring tools available, there is still uncertainty in the area beyond the tool's ability to measure accurately. However, we can quantify the uncertainty. If we know how close to, or far from, the true measurement value we may be, the measurement is useful. One way to indicate uncertainty is through the use of significant digits, which has been discussed in previous lessons. Using significant digits, the measurement value is recorded such that every digit shown has been definitively measured, and it's certain. The measurement cannot account for the value of digits that are not reported. In this example, the green digits have been measured. The measurements tell us that their values are known. The gray digits are not known. The measurements or calculations that resulted in these numbers were not precise enough to account for these digits, so they're not considered significant digits. A more definitive way of indicating the uncertainty of a measurement is to use plus-minus notation. In this case, if we're certain that our measurement falls within 0.05 centimeters of our reading, then we're certain the true value falls between 3.79 centimeters and 3.89 centimeters. This can be expressed in two ways. It might be written as a value plus or minus a margin of error, called plus-minus notation, or it may be expressed as a compound inequality, in which case the upper and lower limits of the measurement are given, with the true value falling somewhere in between. Sometimes using significant digits to indicate uncertainty can be misleading in terms of the closeness of the reading to the actual measurement value. The resolution indicated by the smallest increment of the measurement scale may lead the user to believe that the measurement reading is a better estimate of the actual measurement than the instrument can reliably produce. For example, speedometers are often incremented to 1 mile per hour. However, speedometers typically do not display the speed within 1 mile per hour of the actual speed. Sometimes the manufacturer's specifications will give a maximum error that would indicate uncertainty. However, it's sometimes difficult to determine the meaning of specifications when terms such as accuracy, precision, error, and uncertainty are often used interchangeably. When a measurement is critical, the precision and accuracy of the equipment should be checked often to ensure that errors are within acceptable limits. How can we determine, with confidence, how close a measurement is to the true value? There are two distinct terms that are related to uncertainty in measurement: accuracy and precision. Although precision and accuracy are often confused, there is a difference between the meanings of these two terms in the fields of science and engineering. Accuracy indicates how close measurements are to the actual quantity being measured. For example, if you put a 50-pound weight on a bathroom scale, we would consider the scale to be accurate if it reported a weight of 50 pounds. Precision indicates how close together repeated measurements of the same quantity are to each other. A precise bathroom scale would give the same weight each time you stepped on the scale within a short time, even if it did not report your true weight. So if you placed a 50-pound weight on the bathroom scale 5 times and the scale displayed a weight of 47 pounds each time, the scale would be considered precise, but not accurate. It helps to visualize these two terms by thinking about a target. Consider the arrows or dots on the targets to be repeated measurements of a quantity. The first target shows that the arrows or repeated measurements are centered around the center of the target, the actual value. So on the whole, the measurements are fairly close to the target measurement, making the measuring device accurate. But the repeated measurements are not close to each other, so the precision of the measuring device is low. The second target shows that the arrows or repeated measurements are close together, so the precision is high, but the center of the measurements is not close to the target value of the quantity. The third target shows both precision, because the measurements are close together, and accuracy, because the center of the measurements is closer to the target value. Ideally, a measurement device is both accurate and precise. Accuracy is dependent on calibration to a standard. The accuracy of a measurement is its correctness, or how close it is to the accepted value. Poor accuracy tends to result from incorrect measurement procedures or flawed malfunctioning equipment. Poor accuracy is associated with systematic errors, such as a student continually taking measurements with a ruler, but beginning the measurement at the end of the ruler instead of at the 0 mark. Precision is dependent on the capabilities of the measuring device and its use. Precision measurements are reproducible. In other words, the measurement can be repeated many times and result in the same or nearly the same value. Poor precision is associated with random error, such as two students seeing a measurement that falls between increments on the scale and one choosing to round up while the other chooses to round down. This sort of error is easier to avoid with more precise measuring tools. To illustrate the difference between these two terms, let's look at an example. Two groups of students each measure the length of a credit card 4 times. Group A measures with a plastic ruler, and Group B measures with a precision measuring instrument called a dial caliper. The results are shown in the table. Let's look at Group A's data plotted on a number line. Now let's see Group B's data added to the same number line. Group A's data ranges from 85.0 to 85.2 millimeters. Group B's data ranges from 85.298 to 85.301 millimeters. The accepted value of the measurement is 85.105 millimeters. By looking at the number line, we can see that Group A's data is more accurate because, on the whole, the data points are closer to the accepted value. Group B's data is more precise because the recorded values are closer to each other than Group A's data points, even though they are less accurate. The failure in accuracy could have been caused by a systematic error, such as the dial caliper not being calibrated. The students might find that when they shut the caliper, the dial reads a number higher than 0, which would explain why their measurements consistently came out much higher than the actual length of the credit card. We can determine the relative precision and accuracy of the credit card measurements intuitively by looking at the data, but we can actually quantify the precision and accuracy of the data to make more meaningful sense of the two groups of measurements. Accuracy can be represented numerically by the error in the measurement. The error is the difference between the measured value and the accepted value. As a measured value gets further and further from the accepted value, the error gets larger and larger, and the accuracy gets lower and lower. It's common practice to take several measurements of important quantities to help reduce the potential for avoidable errors in the measurements. If a measurement is obviously much different than the other more consistent results, the outlier can be eliminated from the data, or new measurements can be taken to verify the results. When multiple measurements are taken, the mean of the measurements is used as the measured value. The mean of the credit card measurements by Group A is 85.10 millimeters. The mean of the credit card measurements performed by Group B is 85.2998 millimeters. Let's calculate the error of Group A's measurement. We subtract the accepted value from the mean of the measured values and find the error of Group A to be negative 0.005 millimeters. The space on the number line between the mean of the measurements and the accepted value represents Group A's error. It's important to remember that error is an absolute value, so although in this case we calculated the error to be a negative number, we would report the error as simply 0.005, the difference between the mean and the accepted value. Now let's calculate the error of Group B's measurements. We subtract the accepted value from the mean of the measured values and find the error of Group B to be 0.1948 millimeters. The distance between the red line and the green line is clearly much greater than the distance between the blue and green lines. But this difference in error might not always be so apparent, so it helps to know how to calculate and quantify this value when comparing two sets of data. Which group's measurements were more accurate? Group A's error was far less than Group B's, making Group A's measurements the most accurate. Precision is related to the variation of the data. With a quick look at the number line, it seems that Group A's data varies much more widely than Group B's. There are several ways to indicate precision. This type of data is very often assumed to be normally distributed. If we assume that the measurement data from each student is normally distributed, one method to quantify precision involves the standard deviation of the repeated measurements. The standard deviation of a data set is an easy way to quantify and compare the precision of the data against another set. In this case, the standard deviation of the credit card measurements taken by Group A is 0.08 millimeters. The standard deviation of the measurements performed by Group B is 0.0015 millimeters. Using the standard deviation of the data, we can easily see that Group B's measurements were much more precise or repeatable than Group A's, even though Group A's measurements were more accurate. You can use the empirical rule to quantify precision based on a set of measurement data for a specific quantity. Precision can be indicated by giving a range of values using plus-minus notation, and a level of confidence that the true measurement value is within that range. So for example, you can state with 68% confidence that the true value of a measurement is within one standard deviation based on multiple measurements of that quantity. Likewise, you can state with 95% confidence that the true value of a measurement is within two standard deviations of the mean. If we wanted to express the precision of Group A's data at the 68% confidence level, we would use the empirical rule to add and subtract one standard deviation from the mean to find the upper and lower limits of the confidence interval. Student A's data has a mean of 85.10 and a standard deviation of 0.08. Therefore, we can write a statement to indicate the precision of the measurements as 85.10 plus or minus 0.08 millimeters. The range can also be written as a compound inequality that specifies the minimum and maximum value of the quantity at a given confidence level. We would follow the same procedure to write a statement indicating the precision with 95% confidence. In this case, you'll add and subtract two standard deviations from the mean to obtain the minimum and maximum values of the range. Each of these graphs tells a different story about the precision and accuracy of the data in the set. Graph A shows the mean of the data far from the accepted value, so its accuracy is low. But the data seems to be clustered close together, so the precision of the measurements is relatively high. Graph B shows the mean very close to the true value of the measurement, which indicates high accuracy, and the data appears to be close together, indicating high precision. Graph C shows a mean that's far from the true value, and the data appears to be spread out from the center quite far. This indicates low accuracy and low precision. Graph D shows a mean value close to the true value, indicating high accuracy, but the data appears to be spread out far from the mean, indicating low precision. Hopefully this series has helped you understand a lot about statistics and how they can be useful in engineering to quantify and compare data to improve the quality of products and the efficiency of the processes used to make them. Thanks for watching.